In early lectures, we have seen two different ways of introducing analytic functions. Either you consider analytic functions to be functions that satisfy the Cauchy-Riemann equations, or you can use the approach from vector analysis and say that an analytic function is a function for which the path integration is locally independent of the path. In this lecture, we'll consider the third way of characterizing analytic functions, namely by power series expansions. So we have a power series. It's an expression of this form. And it's easy to see that every such power series will have a domain of convergence, which is essentially a circle or a disk. So if you have the point Z0 here, the set of points where this expression converges will be a circle or a disk centered at that point, including some of the points on the boundary. And if you consider any strictly smaller disk here now, this convergence will be uniform, and you can also prove that you can, for example, integrate and differentiate this series under the integral sign here now. I won't go into those details in this lecture, but that's in principle, you can prove it by elementary methods then. So in particular, you see that you can take the complex derivative of this just by differentiating every term separately. So since all the terms are polynomial in Z, the complex derivative of each term will be 0, and you conclude that this is an analytic function then. So every power series gives you an analytic function inside the domain of convergence, you can say. But what is remarkable is that the other direction of this is also true. If you have an analytic function, you can always write it as a power series in some neighborhood of any given point in the domain where it's analytic. And this is what we'll see now. And it also actually follows from the Cauchy integral formula. So suppose now that we have this point Z0 here, and we choose a circle here now with radius r, say, and we assume that this disk here is strictly inside the domain where the function is analytic. So in particular, it will be continuous on this closed disk then. Now, then we know that we can write for any point inside the circle, we can write f of z is equal to 1 over 2 pi I times the integral CR of f of w divided by w minus z dw. And once we have this, we can now rewrite it in the following way. First trivial step here now is that we add and subtract the term Z0 in the denominator. So we write it as W minus Z0 minus Z minus Z0, like that. Then we have subtracted Z0 and added Z0 there, and dW. And then we extract, so to speak, this factor and put it outside the this quotient here now. So what we get then is well, f of w, and then divided by w minus z naught. And what will be left here now is then 1 divided by 1, and then minus z naught, z minus z naught divided by w minus z naught. And then we also have a w like that. And the point is now that for every z in this disk, the numerator here will be, the absolute value of the numerator will be strictly smaller than the absolute value of the denominator, because z is a point inside here now, and w will be on the boundary of this circle now. So this has absolute value less than 1. And recall that if we have an expression like this, well, let's use a Greek z here now, then this can be written as a power series like this. This is just the formula for summing a geometric series. So if we now do this backwards, we introduce, replace this quotient here by this series. What we get is then the following: 1 over 2 pi I, and then integral c over cr, and then we have f of w divided by w minus z naught, and then we get this sum here now. K goes from 0 to infinity of this quotient, which is z minus z naught divided by w minus z naught, and then dw then. And now we see that if we just to the power k here now, like that. And now we see that we can just rewrite this by actually moving the summation outside here. Remember we said that you could integrate or differentiate power series term by term. And if you do use the same arguing backwards, so to speak, you can move also this, or actually you can integrate here term by term, which then means that you can move the summation sign outside here. So you get sum k goes from 0 to infinity of, and then you get this expression 1 over 2 pi I integral over cr, and then you have f of w, and then we have one factor w minus z naught here in the denominator, but we also have k similar factors here, so you can actually write it as w minus z naught to the power k plus 1, and then we have are left with this expression here now, but that does not depend on w, so we can move it outside this this integral, but put it on the other end here now. So we'll have here now z minus z naught to the power k. And so you see what we have arrived at is really a power series expansion where this is the coefficient. This is what I have denoted by a k up there. So we get the formula that f of z is equal to the power series k goes from 0 to infinity of ak z minus z naught to the power k, where ak is given now by 1 over 2 pi I times the integral over cr of f of w divided by w minus z naught to the power k plus 1 dw. So this is really the idea behind power series expansion, and sort of explains why analytic functions can be written as power series. Of course, there are some technical details to check here now, but I won't go into that in this lecture. What I do want to do is to show a generalization of this. In some situations, it could be that you want to expand a function, but in a domain, say inside a circle, but you don't really know that the function is analytic everywhere here now. So, for example, it could be that the function is singular in some way at the origin. For example, let's take the function e to the power 1 over z, like this. This function is perfectly analytic in any disk like this around the origin if you remove the origin itself. On the other hand, it's clear that this can be expanded, perhaps not in powers of z, but in powers of 1 over z in the following way. Here I actually only just simply used the ordinary power series expansion of e to the z, but instead of z I've written 1 over z, and then you get this formula. So then it's reasonable to ask, if you have a function which is analytic in some annulus like this, in the region between two circles here, is there a way of expanding the function in this region, even if it's not analytic in here, and if you don't know anything about its properties outside here? And the answer is yes. And the kind of series you get are called Laurent series. So how do you find such an expansion? Well, the idea is that you cannot really, if you choose a curve like this, you cannot really apply Cauchy's integral theorem because the function is not analytic in here. But if you, instead of this curve, now modify it a little bit and go around in this way up here, then you actually have a domain where the Cauchy integral formula is valid because, well, it's simply connected actually. And then the idea is that you sort of take the limit when these two parts here now sort of, well, shrink to, well, you take the limit when they converge to each other. And since you integrate along in different directions, they will cancel out. And what you're left with is that you can, for any z in this, in between these circles, then you can write f of z as the difference between two integrals. First, the integral over the outer curve here now, let's call that gamma 1 of f of w divided by w minus z, then dw. But then you also get an integral in here. And so if you use the orientation which goes clockwise here now, you should get plus next integral here now. But if I call this curve gamma 2 and use the orientation counterclockwise, then you instead get a minus sign here. So you will get f of w divided by w minus z dw over gamma 2. And this actually gives you a representation of the analytic function in the region between these two circles. So for simplicity now, let's suppose that these circles are centered at the origin now. So the region we're considering here, omega, is actually the set of all z which satisfy the property that the absolute value of z is larger than small r here, and less than capital R then. And then we'll see now that this formula will give you an expansion now including both positive and negative powers of Z. So the first part here, if you take the integral over gamma 1, it's actually more or less the same computation we did with the ordinary power series expansion before here now. So in this case, you can just rewrite this as, 1 over 2 pi I. Then you have 1 over 2 pi I. And then you rewrite this as 1 over Z. 1 over W here now. And you have up here you have f of W. And then you get here W divided by 1 minus Z over W. And then you replace this by the geometric power series expansion, and then you get 1 over 2 pi I times the integral over gamma 1 of f of W divided by W times the series k goes from 0 to infinity of Z divided by W to the power k dW. And this can then be rewritten as before as the sum k goes from 0 to infinity of 1 over 2 pi I times the integral over gamma 1 of f of W divided by, and now we have W to the power k plus 1, and then we have dW, and then we have zeta to the power k. So this term here gives you just the ordinary, something which looks like an ordinary power series, just as we have before. But if we now take the second term, minus integral over gamma 2 of f of W divided by W minus Z dW, then you can also expand this. But instead here now, instead of sort of extracting 1 over W, what you do is that you extract minus 1 over Z, which then gives you the following expression then. You get f of W, and then you get Z, and sorry, this should be 1 over 2 pi I here also, of course. And then you get here dW and 1 minus, and then here the rows will be inverted, so to speak, so you get W divided by Z. Because now on gamma 2, of course, in this situation, if W belongs to gamma 2 and Z is in this region between, then the absolute value of Z will be larger than the absolute value of W. So therefore this number here will always have absolute value less than 1, which again means that we can write this as a power series now. So you get 1 over 2 pi I integral over gamma 2 of f of W, and then divided by Z, and then you get the sum k goes from 0 to infinity of W divided by Z to the power k, and then dW then. And now again, you see that by absolute convergence and so on, you can move the summation outside here now, and you get a sum from 0 to infinity of expression like this: 1 over 2 pi I times integral over gamma 2 of f of w, and then you see now that let me write this slightly differently. Then you get here now f of w, and then you have this power w to the k here now, and then dw, and then you get the extra factor here, which is z 1 over z to the power k, and then you have one extra 1 over z over there, so you get z to the power minus k minus 1, you might say. So the first term here will give you ordinary power series expansion. The second term will give you a power series in 1 over z. So if we now sum this up, so what we have arrived at now is really the result that every analytic function defined in such an annular domain can be written as an infinite sum where the summation actually goes from minus infinity to plus infinity with certain coefficients a, k here now. And where, well, actually I've done the case where the center of the region was at the origin, but you can do this as well at any point then. And then you get this kind of expansion if your region, your annulus is centered at Z0. And the coefficients here, they are given by integrals in this way. You get f of w divided by w minus z0 to the power k plus 1 here now, dw. So remember that for 1/2 of the terms, those with positive k here, we use the outer circle for integrating here now, what we call gamma 1 then. And for the other part, you use the inner circle, which we call gamma 2. But once we have arrived at this formula, you see that it doesn't really matter if we integrate along around gamma 1 or gamma 2 anymore, because by the Cauchy integral theorem you can move the path of integration to any circle in between, if you like. So this is really the Laurent expansion here now of an analytic function in such a domain. So let me just take a very trivial example here as our last point then. So consider the function 1 divided by 1 over z then. Of course, in the region where absolute value of z is equal to is less than 1, you have the ordinary expansion just from the geometric series expansion. But if you want to study this function outside this disk, in the region where z absolute is larger than 1, then you can use a different expansion, which is then Laurent expansion, which you get in the following way. You take the function 1 over z, and then you just from this extract 1 over z from the denominator, and you're left with 1 divided by, 1 over z minus 1, like this, which you then rewrite as minus 1 over z, and then times 1 divided by 1 minus 1 over z. And in this region, of course, this will be less than 1 here now. So this can then be written as minus minus 1 over z times the infinite series, k goes from 0 to infinity of 1 over z to the power k. And this, of course, can then be written as minus some k goes from 0 to infinity of z to the power minus k minus 1, if you like. And of course, by changing k to minus k, you can write it as a summation from minus infinity to minus 1, if you like, instead. But this is really the usual way of writing the expansion. So the result is that for a given analytic function, you may have several expansions which are valid in different regions then. In this case, there are just 2 regions, and they're very simple, but in general, you have many different Laurent expansions of the same function.